Hello everyone. My name is Badanda Shuvo. I am an MEC student at the University of Alberta. I am working with my supervisor, Professor Dr. Minglu. Today I am going to present my work on lean construction planning subject to the variations in detailed features of fabricated bridge girders. So let's start. Fabrication processes may be considered as one of the most complex undertaking in any industry. So here comes the question first, why this is so challenging and complicated. So if we talk about the shop scheduling in fabrication, unlike other industries where the products are identical, here in shop fabrication shops, the products are more unique and there are lots of variations among themselves. And also there is little chance of automation and they are most prone to human error. Beside these, you can say that the resources are mostly shared among different activities. So there is a lot of scope for idling and waiting time for the workers. So let's assume a scenario where there are two guys. So the name of one person is Spencer, who is in charge of scheduling, and there is another guy whose name is Chris, who is the shop manager. So they kind of remain busy in the shop, but Spencer needs information about the production capacity and skip sequencing and different kind of scheduling information from Chris. But Chris knows that it's very hard for him to give this information to Spencer because most of them are continuously changing and they are kind of uncertain. So here our research comes handy because the motivation behind our research is to develop a valid, simple virtual plant which will be easily accessible by both of them, and it will be continuously changing according to the changes that are being made throughout the project. So for our case study, we took the scenario of a steel girder fabrication shop located near Edmonton, Alberta. You can see the girder configuration here. So our model has been developed based on these configurations, and there are 15 girders which are making up 5 girder lines. And you can see that there are 4 different types of girders which have been defined in this configuration. So this classification was based on the similarities of their attributes and their specifications. And you can see that there have been different different symbols that have been assigned based on their types. So here I want to show you the specifications that we took into account for these classifications. Now I am going to talk about the variations that take place in this attribute. So first of all, when you try to dig into the girders, so we saw that these variations normally come from their length, the number of the field splice, the stiffener complexity, and many more. And for the flange, these variations normally exist due to their length, their width, their thickness, the number of frills, and the flange splices. And for the wave, we just saw the similar pattern. Here, the variations normally depend on their length, their width, their thickness, and their number. So you can notice that the variations are mostly dictated by their structural design and the positioning of these girders, which really make them unique than one another. So how we are dealing these specific attributes and defining these different types of girders is going to be a deciding factor in the later phase. So now let's look at the operations that took place in a fabrication shop. So steel plates are normally transformed into steel girders as per the engineering design in a constant place in the fabrication shop. So these workflows can be divided into different processes and different activities. So when this overall operation is designed, it is normally designed in event diagram. So when we try to adjust these resource constants and try to include these error links, it kind of turns big and messy. You can see like there are so many unique network models you have to assign to each unique girder, and in that case it will turn more messy. And if one mistake takes place in the whole network model, it kind of becomes impossible for the shop manager to fix that. So here, when these conventional AON or say CPM, when they don't work, our model will give Chris the perfect solution. So when the shop manager will have this complexity problem or the uncertainty problem, he will take the help from DSOF, which will give him a user-friendly interface and solves all the problems he has. So what does DSOF work? So DSOF works on a 3-tier simulation framework, which facilitates the streamline modeling to create a logic-driven and feature-based model in the current application domain. So the framework separates the modeling parameters into frequently need to change at the top tier, the occasional need to change at the middle tier, and never need to change at the bottom tier. So with this setup, the modeler would have an AI-like interface to set up, which will require almost no additional knowledge for him to learn. So the bottom tier is actually the simulation engine, which is responsible for manipulating all the simulation events and constraints as specified in the top and middle tiers. It kind of provides the analytical power of simulation analysis and brings each resource and each constraint into order along the timeline of simulation. And the middle tier parameters only need to change when the shop configuration undergoes any major overhaul. It is also adaptable to the changes in processing logic, time, and resource constraints based on the Girder features. And the top tier normally has a simple interface to define the material specifications and the engineering design attributes. So any change that takes place at the top tier dictates the likely scenarios of sequencing girders for fabrication. So you can see you almost require no basic knowledge in simulation modeling because it will adjust automatically according to the data you give to the model. So here the slide shows the different likely scenarios that this software can make out from the data you give. So it is really very easy for the shop manager to change the fabrication sequence, to play with them. And based on that, you can choose the perfect combination you want. And it will give the number of journeymen you require, the project duration needed, and the utilization rate. So SDSA can adapt itself according to the changes you make, and it will kind of solve all the questions that Chris has inside his mind. So here we are showing the detailed start and finish schedule with SDSA for our project. So it can be said that SDSA model kind of mimics the common CPM model used in construction planning, but it requires less effort and more user-friendly. So unlike other platforms like MS Project or P6, it automatically accumulates the data you gave, and you can see that these shape and numbers are not like the number that we can guess. It is automatically predicted by running the virtual plant simulation, and they can change in a different setting or sequence you want. So here you can see that the duration and the start and finish schedule are kind of different for each type of girder. So according to the current practice, the shop manager normally assume that all girders in the shop will have the same duration. But here you can see that the duration normally vary based on the type of the girders. So each girder line needs different amount of days to be completed, depending on the specific properties and their attributes. Also, if you look at the lag time, you can see that between two girders, the lag time is different for each type of girders. DISA normally shows these variations in the lag time based on their types and their properties and their attributes. So from these two tables, it's kind of clear that shop fabrication duration and start to start lags between two different girders have broad variations, and they need to be accounted and they need to be proper paid attention. So the girder fabrication duration, or the SS lag, or the start to start lag, depend on the sequence of the loading girders, their type of girders, and the production capacity of the shop. So based on the deadline you have, the software will help you choose the maximum number of girders that can be fabricated over a week or a month. So here is the framework that was developed in SDSA, which can show that a maximum of 5 girders can be processed concurrently at any given time. So where Aeon is exploding in size due to the constraints, SDSA normally taking all the considerations into its account, and it is giving you a more predictable and more effective and linear solution. So to summarize these contributions, the contributions of this study, we can say that this research normally presented a simulation case of planing bridge girder fabrication to eliminate the unevenness hidden in the girder fabrication. And it has tried to come with a linear approach for the bridge girder fabrication and installation. So we can say that if we can map these outcomes or sequences electronically and automate tasks that were once done manually, we strongly believe that this will be a blessing for this error-prone and volatile construction industry. So in order to learn more about SDSA, you can check this relevant work done by my professor and his PhD student, Manjuru. Also, I would like to thank Supreme Group for their collaboration throughout the research. The research was funded by Natural Science and Engineering Research Council, and I also like to thank my professor for his assistance toward the research. So thank you for listening to my presentation. If you have any question, please let me know later. Thank you and stay safe.